All right, so welcome everybody, and in particular, welcome our excellent speaker today, Shie Mannor. So it's a very easy job to introduce Shie because everybody knows him. He has made many, many important contributions to both the practical and theoretical side of reinforcement learning and in learning theory in general. So Shie has a pretty colorful CV. I'm mostly going to highlight that he's a professor at the Technion since 2008. Before that, he was a professor at McGill University in Canada and a postdoc at MIT, and he did his PhD at the Technion in 2002. And like I said, he made many important contributions to the theory of reinforcement learning. And what he's going to talk about today is some theoretical results regarding trust region policy optimization. So please welcome Shie.
So thank you, Gerli and Chaba. Thanks to the organizer for that. I just want to take a minute to thank you for organizing this whole series. It's really been a pleasure. And I look forward to the future talks, and I think we should continue with that even after this coronavirus madness is over. I think it's really fun and enriching for everybody. Today I'm going to talk about trust region policy optimization, what's known as TRPO. I'm going to present two papers. Originally, I thought about presenting just one. The first one is going to focus on global convergence and faster rates. That's a AAAI paper. The second one is a recently accepted ICML paper that is basically introducing an algorithm which we call policy optimization mirror descent, POMD. And those are algorithms that are really doing trust region optimization for reinforcement learning, and we'll show the connection between the celebrated mirror descent algorithm, which is a classical algorithm for convex optimization, and RL. Before I start, I want to mention that you see that there are two names here, Lior, Shani, and Yonathan, Efroni. Those are my two excellent PhD students who did all the work. So I'm just basically, if you have really hard questions, you should ask them. And just last before least, as you can see here, there is the Technion. There are a group at the Technion, the Reinforcement Learning Research Lab, Mark, but also NVIDIA. And I have joined NVIDIA research recently, and seen that like NVIDIA is serious about RL. So let's start. So this talk is about TRPO, and TRPO is an algorithm that was proposed 5 years ago, has gained tremendous popularity, works pretty well. And the question is, why did it work, and is it really a justified RL algorithm? And what we'll show in the first half of this talk is that the answer is positive. TRPO is a justified RL algorithm, and you can justify it by viewing it from a convex optimization perspective. So the main contribution of this work are that we show that a version of TRPO converges to the global optimum with a rate of 1 over square root of n, where n is the number of iterations. We show that for a slightly modified regularized MDP, so we slightly change the rules, but not by much, we can get even faster convergence, which is possibly the fastest convergence rate you can imagine. And then we reinforce the connection between convex optimization and RL. This has been around for a while, but what we're doing, I think, is we're really tying the knot, and we show that RL algorithms can be viewed from a convex optimization perspective. And you know, there is a star, there's a defined talk, defined details. So this talk is really about finite state and finite action spaces. So if you're looking for something more exciting and larger, then you'll have to wait for next year's talk. So everything is finite state, finite action spaces from now on. So let's revisit policy optimization. So I want to introduce notations. So we have for a given policy pi k, we have what is known as the advantage function. So this is basically the difference between for a new policy pi, what you'd get from activating the Bellman operator for a fixed policy over the value function of the policy pi k. So this is the advantage of pi over pi k the one-step advantage, you can, in principle, if you would iterate the operator that is here, the t pi lambda, then you would get the actual advantage. But for now, we're only looking at the one-step advantage. So this is a policy optimization. Basically, you solve the one-step advantage function, and you reiterate and reiterate until you get convergence. So this is a way to present a classical policy iteration algorithm. You may ask, what is the lambda notion here? So we'll introduce the lambda later. So for now, don't worry about it. You can ignore it for now. By the way, throughout this talk, I'm going to consider cost rather than reward, so I can get latecomer confused. So this is really just the cost of the immediate cost plus discount factors time the next state value function according to the distribution of pi. So what is the idea behind trust region optimization? The idea is that, or so it is said, we keep the current and the foreign policies close. So we're not just optimizing the one-step advantage. We want to optimize one-step advantage, either subject to a constraint on the KL divergence between the new policy and the old policy, or through giving a penalty for very large divergence. Our objective today is going to be a scalar objective. So basically, we scalarize the value function. So in this, the notion here is that we look for expectation when the states are distributed according to some measure mu of the value function. And we can, because everything is finite, we can write it to the product. So we'll look at the scalar objective, and we'll discuss what should mu be later on. So in the original TRPO paper, the paper with more than 2,000 citations, there are two versions of the TRPO. One is based on what's known as conservative policy iteration, CPI, and that's what's written here. So the next policy belongs to the set of minimizers. So to remind you, we're minimizing here. There is a cost. Of the expected advantage plus TK is a learning rate, so 1/TK times the maximum of the DKL, the KL divergence between pi and pi k. So this is based on CPI, and to remind you that I think by now it's fair to call it seminal work of Kakade and Langford in defining conservative policy iteration. It's a policy iteration step where you don't go very far, but you go far enough so that you still improve, but you don't there is no way for you to not improve. So it's a version of policy iteration that is you can actually you can use the advantage function, and you're guaranteed to improve at any step. So that's the first version. In the original TRPO paper, they prove convergence, but there's a problem with the optimization because you need to solve this maximization over S of the DKL, and that's not necessarily easy to do because it sort of couples between the optimization of the advantage, which is the first half, and the second half, which is you have to take a maximum over all states. And then there is another version, which is approximation of the first one. And here, instead of looking at the max, we replace the max with this orange term, which is the expected according to expectation according to mu of the KL divergence between pi and pi k. So that's basically the version there. And for this version, there were no convergence guarantees in that paper. And that's essentially what is used in TRPO, and it's not very difficult to implement. So the algorithm itself, maybe you've seen it in a slightly different version where you have, instead of having the plus of the expectation of the DKL, you've seen it with a constraint on the DKL. This is essentially the same. So there really is no big difference. It's a difference of scaling, and we can discuss later on which one is better.
Sorry, Shai, can I have a quick question?
Yeah.
So here in the expectation that you showed, this is taken with respect to mu, which is this distribution that you use for evaluation.
Right.
Whereas I think in the TRPO paper, they have an expectation that is with respect to the state distribution of the current policy. No? Am I wrong there? That's really like mu k.
I think it's mu k, but I don't think it matters much, to be honest. But what is important is that we replace the max with something that we can actually sample.
Right. Yeah. Absolutely.
So there was a question whether this is PPO or TRPO, or like what's the difference between the two? Are you going to elaborate on that?
I mean, this is what appears in the paper. It's essentially the TRPO algorithm. The relation, we can talk about the relation with the PPO, which is also a very much related algorithm. But if that's okay, let me progress a little bit, because while I promised Chava that I'll be done before the time, I think now I was overly optimistic.
All right, please go ahead. Sorry.
It's okay. So what we show is that the practical version of TRPO, the second one, is really a version of mirror descent algorithm, the celebrated mirror descent algorithm to RL. And at the result, we get a feasible algorithm and a global convergence guarantee that can be used. And then again, I just mentioned that you can. We'll do it from the penalty version. You can redo the analysis from a constraint formulation. This is a matter of taste, I think more than anything else. So from now on, let's ignore the constraint version. So the version where you optimize the advantage subject to a constraint on the DKL, and just look at the penalty version. Okay, so. The way to do it is to adapt trust region methods from convex optimization to RL, and that what we'll show now is we'll briefly explain trust region methods, and then we'll try to draw the synergy and try to explain how they're related to reinforcement learning. So the classical convex optimization problem, you want to solve to find x star that minimizes a convex function f of x over a convex set C. And this is sort of a celebrated classical optimization problem studied at length in machine learning and other fields. And there are several ways to do it, but we'll talk today about gradient methods. So there is a so-called conditional gradient descent, or also known as the Frank-Wolf, the projected gradient descent, and exponentiated gradient descent, and they're written here. So I'll just explain what each of them is doing. The conditional gradient descent, which is what's written here, is an iterate where you have a learning rate. So there is always a learning rate here, TK, and you modify your iterative solution so that it moves in the right direction, and then to figure out what the right direction is, you have to solve this optimization problem, which is a linear optimization problem. So this is why it's called conditional gradient descent, because you keep solving this problem. There is another algorithm called projected gradient descent. Here you need to be able to project onto C. So if C is a convenient set to project on, that might be a good algorithm to use. And then you look at your value minus the learning rate times the gradient. And then there is the exponentiated gradient descent, where your modification is proportional to e to the power of learning rate times the gradient. So those are algorithms from convex optimization. I mean, the last two are known as mirror descent algorithms, and there are other mirror descent algorithms. And what we're going to do is we're going to show that these algorithms are actually familiar to us. And in fact, we've seen them in the previous slides. Before that, there's just one comment about strong convexity. So a convex function is strongly convex if essentially it is lower bounded by a parabola, or if its Hessian is lower bounded by n times the identity matrix. So basically, there is a quadratic term that lower bounds the growth of f, and if the f itself is not continuously differentiable twice, then the term below, the equation below, shows you what it should be. So strong convexity is useful because when you have strong convexity, you can get faster convergence rates. And now we'll introduce another term, which I believe most of you have seen, but just in case this is not known, there is something we call the Bregman Divergence. So the Bregman Divergence is a way to take a strongly convex function, in this case W, and create a distance measure. So this BW of x and y is a distance measure. And it turned out that for strongly convex functions, it is a proper one. So if you start with, for example, Euclidean norms for W, for the strongly convex function, then you'll get a Euclidean distance. If you start from the negative entropy, then the Bregman divergence is going to be the KL divergence. And I think there are potentially other W's that are used, but I think those two are mostly used. And it's a pretty interesting question whether there is something else to be said about RL algorithms for that. Okay, so mirror descent in convex optimization. Let's try to write the iterate. So to iterate the trust region method, basically the iterate at time at iteration k+1. You minimize over x of a linearized version. So this is the first term is the linear approximation of the objective. The brackets here are inner product. So this is the gradient of f at xk, comma x minus ak, the linear version, plus the second term, which is a learning rate. Remember, tk is our learning rate, times the Bregman divergence between x and xk. And just note that the minimization is over everything. So you minimize over the yellow, I guess orange term plus the blue term. What is the interesting here is that you can think about it from an intuitive perspective as you want to move in the right direction, but you don't want to move too far. That's why it's called the trust region optimization, because basically you want to trust the points that you're using. Okay, so if you'll use the Bregman divergence to be the Euclidean distance, that you're going to end up with projected gradient descent. And if you'll use KL divergence as a Bregman distance, then you're going to get to exponentiated gradient descent. So basically, you can choose either one, but then you should know what you're choosing. And that is going to lead to one of those algorithms that are all celebrated and well known in the community. So so far we've done a small detour to convex optimization. Now just let me share some results. So those are famous results in convex optimization. That if you have a convex problem, then you get a order of square root of n convergence, and if you have a strongly convex function, then you get order of 1 over n. And so basically, the way we write things here, that we want x star of lambda in the case of where f is not necessarily strongly convex, we add this lambda gx and we modify the problem that we're trying to solve. So the way you should think about it is that when I'm solving this problem, that is not the original one. So originally I want to solve argmin of fx, but for reason of the need for speed, I add to it lambda times g of x, and there I'm solving a slightly different problem. You can tie the connection. You can link the connection between x lambda star and x star. according to the size of lambda and some properties of G, but that's not the main issue that we want to deal with today. But of course, we note that when you do that, you add bias because you don't solve the problem that you actually wanted to solve originally. Okay. So now that we've done a crash course in convex optimization, let's go back to reinforcement learning and let's see what are the issues that we can actually solve with our newfound insights from convex optimization. So in convex optimization, we saw three algorithms: conditional gradient descent, projected gradient descent, and exponential gradient descent. Each of them has a somewhat different iteration. And in RL, what we'll show, or at least argue, that if you're using or the equivalent of Frank Wolf is a CPI, the equivalent of projected gradient descent is a version of projected policy gradient, and of exponential the gradient descent is what we call non-Euclidean TRPO, and we discuss it. And of course, this is not a new algorithm. This algorithm has been around in the last 5 years. So basically, what the take-home message that you should have at this point in time is that if you know how to solve convex optimization problems, we claim that you can do, or analyze at least, some reinforcement learning problems. Okay. But here is the problem. RL is not convex in the policy space. And this is a very unfortunate fact of life. And the question is, okay, why is RL not convex? It's for every state, the optimization problem, of course, is convex. But once you take multiple states and you look and remember that we're talking about finite state, finite action, everything is in principle simple, then there is no convexity in the simplex over action to the power of S. So the question that we're asking, like, okay, can we still get a global convergence with the same rate? So in convex optimization, when you have convex sets, we are able to get 1/√n. When you had strongly convex objective, we're able to get 1/n. So the question is if we can repeat that. And especially the question is, what would be the equivalent in MDP terms? And obviously, we're not going to, for the strongly convex case, we're not going to solve MDPs anymore. We're going to solve some other creature which is close but not exactly the same. So what we're going to do in the next few minutes is we're trying to explain what is in this and those errors, those dashed errors here. Okay, so so regularized MDPs, we analyze those, and this is just we modify the reward or the cost by adding a regularization term. Note that this is for a given policy, and this is the original reward plus lambda, which is a variable, times some Bregman distance that is, you can think about it as the regularizer. And I think the most common it would be is to think about the negative entropy. So this is the regularized MDPs. I think that they have been around for quite some time. Okay, so our objective is to solve this argmin of to find the pi that minimizes this expectation where eta is distributed according to mu of the value function for pi. And our method is to solve iteratively trust region problems. And there is an assumption that we make here, and this assumption is it may look harmless, but it's not really harmless. And that's a finite concentrability coefficient assumption. So because this assumption is problematic, let me dive into it. So this is what's known as a concentrability coefficient. So we denote by C pi star. And it's defined here. So let me explain that in words. D mu pi is I mean, the formula is here, but what it represents is, suppose you start from a distribution mu, and then you use policy pi, what will be your discounted state action frequencies? and then you divide by nu, which is your restart policy, and often mu and nu are the same policy. So we require that this ratio is finite for every state. And this might look harmless, but let's think about for a minute what it means. It means for that the policy nu has a non-zero probability of being in every state that is visited by the optimal policy. So if the optimal policy is such that I mean somehow I know that nu does not nu of every state is non-zero, that it means that I automatically explores every state that is visited by the optimal policy. So one way to think about it is, suppose that I do solve an episodic problem and I have restarts, and wherever I restart, I use nu to find the initial state. Then if I do that, then there is a finite concentrability coefficient assumption, then really doesn't matter much, because I'm going to visit all states that the optimal policies cares about all the time. So I don't need to explore, because exploration is done. I get exploration for free. And there are works showing that this is essentially the best concentrability coefficient, in the sense that it's when other concentrability coefficients are infinite, this could be finite, but not vice versa.
So
this is,
we got a bunch of questions on the chat. Basically, they are asking the rows of mu and nu, right? Yeah. But I guess maybe the next slides are gonna.
Yeah. So I think it's fair to say that in most practical cases, or most interesting cases, mu and nu are the same. So basically, you should think about this nu as your restart model. So you restart to whenever an episode restarts, it restarts to distribution of nu.
So basically, when you're running the algorithm online, this is going to be the start state distribution that you're sending from.
Exactly.
Okay, good. Yeah.
So this is why I'm saying you don't need to deal with exploration, because somebody hands you exploration for free, essentially. So let's look at mirror descent. So mirror descent, we have two parts: a linear approximation plus Bregman divergence. So the blue part is a linear approximation. So this is I mean, I'm writing it as we would write mirror descent. So it's a gradient of pi, according to pi, evaluated at pi k of the expected value, and this is inner product with pi minus pi k plus the Bregman divergence term, where c is some scaling of the state space. And if you want to write it more concretely, then now you have the advantage of pi k minus lambda, the Bregman distance, plus this term. So the linear approximation is still going to be here, the advantage function, and essentially this is the algorithm. But at this point you can ask, okay, so what is c? I mean, how do you like, what should be the right scaling for this to work? This is there are two choices of scaling in the original paper. One is as a max scaling. So here, basically, we look at the maximal Bregman divergence, maximal according to between pi and pi k. Then we mean the maximal s, and we use that. And then the problem is that you need to do the max scaling, and that's going to make your problem computationally difficult. But that algorithm is going to lead to a version of CPI, conservative policy iteration, because it will make you move less, because the second term is going to be larger, so you're going to be more conservative in your moves. The second one is what we call adaptive Bregman term. So here we have the expectation here, and that may go back to the question I had before about what is mu. So it's the same mu is used both for the advantage and to the Bregman regularization term. Okay, but now once you think about it for a minute, you'll see that you can collect the Bregman terms, and basically what you'll have here is that this regularization term is going to be according to how frequently you visit state S. And this frequency is really what we called before d mu pi k. So this is what you get here is that by doing this everything in expectation and counting this 1 over tk minus lambda as for every time you visit every state, this is a natural scaling mechanism that you can use. So this is the iterate that we're proposing. And of course, finally, we can do something which is not just plain optimization. We can do some RL, and you can look at pi k plus 1 to equal a sampled version of those terms, and you do exactly the same update that you did in exact TRPO, but instead of you basically look at the average advantage. One thing to note, by the way, if it's not clear, that the minimum is over everything, right? When I do the argmin, I have to take into account both the advantage and the pi here. So the sampling policy is on policy, similar to TRPO. It's just that you modify the Bregman divergence a little bit differently. Okay, and now in terms of theorem, so if we call pi best n to be the best policy after n iterations, and if you use order of a square, a is the number of actions, s is states, gamma is the discount factor, epsilon and delta are the usual PAC epsilon delta. So if you sample that many samples, then for the unregularized version, you'll get convergence in terms of our scalarized objective function that is with rate 1 over square root of n. And here we have a constant which is not very important. So, but this is the main element is the first term. And for the regularized problem, then we get fast rates. So we get 1 over n rates. Of course, we get fast over n rates, but we don't get convergence to the right value. We get convergence to something that depends on lambda. So if we have a regularized MDP with a regularization of lambda, then we're not going to get to V star like we would perhaps like to, but rather to V star lambda. But that's a price to pay for keeping n for converging faster. So this is the principal theorem, and now to complete the picture. So for convex optimization, we get the non-regularized MDP. We get the 1 over square root convergence. And for regularized MDP, we get that our convex optimization is strongly convex, and the rate is therefore 1 over n. So, and then in terms of the sample complexity, so this is a comparison between CPI, TRPO, and regularized TRPO. It's written here, what are the leading terms, but the real issue is that you can get from epsilon to the power of 4 for TRPO and CPI, you can get to epsilon to the power of 3 to the regularized TRPO. So your dependence is improved, and the regularized TRPO, as you would expect, it has a better sample complexity.
So Shai, we do have some questions. So one of the questions asked was that it seems that if you're regularizing, then your dependence on the discount factor gets a little bit worse. Is that a principled reason for that, or like what's going on there?
So I don't think there is a principal reason for that, but this is something that came from the equations. You do get lambda over there, so and lambda is presumably not very large, but yes, I don't know of a principled reason for that.
Right. So there is another question, which is that So how is the non-convexity being handled here at the end of the day? Like, what did we do so that like the non-convexity doesn't hurt us?
So the non-convexity does not hurt us because essentially, I mean, the way the problem is defined is that now we solve everything in terms of pi, but at any given point in time, we have a linearized, very simple linearized problem, and we solved that advantage. Actually, this is a problem that I probably want to get into afterwards because I think it's pretty interesting, and the math here, one has to work out the details. So let's just summarize. So what we showed is a tabular sample-based TRPO is a justified RL algorithm. It's really a natural version of mirror descent, and you get fast or slow rates to global optimum according to whether you regularize or not. So just to recap, basically in convex optimization we have adaptive scaling of proximal terms and mirror descent. That led us to adaptive TRPO. And then we use a projected policy gradient, which is the algorithm that is derived from that, and TRPO, which is a version of uses the conservative policy iteration, and essentially adaptive TRPO. So at this point, what you can ask, so why should the practitioner care? So what we show is that, or what we hint, that entropy regularization can enhance convergence, and I think that those who use SAC in practice can attest to that. And the other issue that you can say, well, should I solve the penalty version of TRPO or should I solve the soft version of TRPO? So the answer, it doesn't matter. Do whatever is easy. Both will lead to the same location if you modify the learning rate properly. And then I want to just, I know it's a theory talk, so I just want to show something about whether or not this is a good algorithm. So the mirror descent version of policy optimization and the TRPO that uses the penalty, I mean, there is a paper that our friends at Facebook published, and essentially it shows that the results are on par. So I'm not sure which one is better. There are experiments where one is better and experiments when another is better. I mean, you can judge for yourself, but the mirror descent policy optimization version is easier to implement because you don't need to solve a constraint optimization problem. So far we talked about essentially optimization only problem with no exploration. And basically what I'm going to talk about now is I'm going to briefly report some recent results from our paper that will appear or will virtually appear at ICML. And we go back to this assumption of finite concentrability coefficient. And remember what it meant. What it meant is that we don't need to deal with exploration because essentially we're guaranteed to visit every state that is worth anything, so that optimal policy visits with a positive probability. And the question is if we can relax this assumption. So we turn our attention to looking at the regret. We're minimizing cost here, so this is why the regret may look a bit different than what some of you are used to. And basically the idea is to explore using optimistic reward and transitions at the same time. And we write the same algorithms for MDPs and for stochastic MDPs and for what's known as online MDPs using the same tricks of that have been used by others, and we get the best rates possible or the best rate we know how to get at least in those problems. So I'm just going to show the algorithm which we call POMD. That's a stochastic case. So here we have episodes, and in every episode, so in episode K, we roll out a trajectory with a current policy pi k. And so we have a rollout, and then for every point in history and for every state in action, we do the optimistic cost with UCB bonus. So basically, the cost here, this is optimism here is minus because we're minimizing, we're looking at cost. And then we do that for every state in action. We compute the value function. This is an inner product of the Q and the pi. And then we do the policy improvement in a very simple way. It's just a mirror descent update, and you have to tweak with the TK here a bit, but that's not too bad. So we do actual mirror descent. We update the counters, and that's the whole algorithms. One thing I have truth in advertisement. I mean, for every state in action and H, or so every element of the horizon, we have to do this update every episode. So basically, we have to do a lot of updates, but on the other end, we will gain in rates. The adversarial POMD. Here, the model is an online model. So you have rewards which are chosen according to an oblivious adversary. And the idea here is essentially very simple. Everything remains the same except for estimation of the cost function. Here we use the same trick that Gurley has used a few years back. So this is an important sampling type of cost estimation. This plus gamma, that gives you sort of a bonus. And we're looking for the policy which is the best model in the confidence interval, and which we solve the Q according to the best model in the interval plus the cost function. And the updates are essentially remain the same. Again, we have to modify for every, we have to do the updates for every state, every action, and every element in the history. So basically, this is the adversarial case. It's almost the same as the stochastic case, but the way we learn the rates and the probabilities is different. Okay, so let's just because of time, let's just summarize the results. So there was O of K is the number of essentially the time. This is the main aspect for which we optimize. Of 2 to the power of thirds for online MDPs with known transitions. So we extend it to unknown transitions, still getting the same K to the power of 2/3 rate. There was an order of 1 over square root of K rate for online MDPs with full information. That's work by Kai et al. And then we extend it to banded feedback and stochastic MDP. So his model is more difficult in the sense that it's an online MDP, but it's more easier that his information is full. And our model is more easy in that it's stochastic, but more difficult in having banded feedback. And we show the table here of known results. At least those are results that were known until recently. One thing to note is that if you're willing to solve an optimization problem that is, I won't know if global is the right name, but a more complicated one, then there are the OREPS framework, and then you get better across the board. But you have to solve an optimization problem as opposed to the simple update that we see here. And this is, I think, a fairly simple update that does not require much. You do have to optimize, at least for this case, for the policy, but this doesn't seem like a very difficult optimization problem. You should be able to do it quite easily. Okay, so what we know that policy gradients like CPI, TRPO, and natural policy gradients, we know that for them, if you only do optimization, you need to assume something like concentrability coefficient is finite. That's a hard assumption. That means that essentially you have access to the optimal policy. However, you can do on-policy updates, and you don't need to learn the model. On the other hand, we know that optimistic policy optimization algorithm like OPPO and RL POMD, they don't need don't need any assumption which is restrictive about exploration. On the other hand, you need to update all action state pairs in each iteration, and essentially you build a model. So the question that you ask is, like, can I get the green parts of both aspects? So can I get an algorithm that has no restrictive assumptions and does on-policy updates, probably in a model-free way, but maybe not necessarily, that is on trajectory and only updates on this trajectory? And at least I do not know the answer for this question, and I would be very happy to learn it. So I think it's my time is essentially up. I want to say some philosophical words. So RL is really about, we think about it from a theory perspective as state, reward, and actions, but you think about it a little bit from a bigger picture, then its state is not something you often have. You often have just observation. Reward is something that we invent. You really have a utility, which is potentially has much longer horizon, and action, that's just our manifestation. Really what you have in physical systems is dynamics. And in terms of the research, then a lot of work should be given to representation. This work has nothing to do with that. Of course, we assume everything is finite and easy, and to unsupervised RL. And one thing I'd like to mention that for agents to scale up, we need awareness. So agents should know how well they're doing. We need robustness. So agents should be able to deal with environment that changes. We need accountability. Agents should be able to explain what they did. Scalability. So you need to be able to work with large problems. And lifecycle consciousness, meaning we need to be able to debug our agents. And the way I view research is that whenever I have a problem, I want to judge it whether it contributes to one of those 5 elements. Today we talked about TRPO, and what we showed is that this algorithm works because it is a mirror descent algorithm, and not because the iterates remains closed. And if you buy this conclusion, then this can lead to scalability, because mirror descent algorithms are extremely efficient and can work for very large problems. So if you'll use this algorithm or modification of it, there is hope to scale for a very large problem. And I thank both of my students, Lior and Yonathan, who are on the job market. So if anyone is interested in fantastic researchers, do contact them, or send me an email and I'll send it to them. And with that, I will conclude. And we're hiring. So if you want to come and you like this kind of job, send me an email. Thank you.
All right.
Hey.
Let's give Shie over to class.
Congratulations.
Yeah, good job.
All right, thank you, Shie. That's fantastic work. So I have a bunch of questions. Mind if I ask a few of those?
Oh.
So this relationship between TRPO and mirror descent and convex optimization, so that has been pointed out a few times in the past. So like I myself had a paper about that. And I think like one interpretation that I found very nice and intuitive about it is that it actually matches this other algorithm that is called the MDP expert algorithm, in which you play exponential weights in every state in an MDP.
Right.
And then this perspective has been used for analyzing this other algorithm that Csaba is behind, this Polytex algorithm. And I think what they did there was sort of similar to what you did here, was sort of to analyze the error propagation in the policy evaluation through the process. So can you say a few words about this comparison, if you have like anything?
I think that essentially both works are doing something which is very similar. To the point where eventually the algorithm is the same algorithm. Like there is no, you cannot play with it beyond that. I think that the main issue is that you want to drive, at least we wanted to drive the analogy to optimization all the way, and actually rederive TRPO as a mirror descent algorithm. And I mean, I think we,
Mm-hmm.
we make a full comparison, and this is a really nice. I mean, we really like the work. Congratulations, Java.
Right. So can you just show me your update rule once again, like how you collect your samples and how you use those to
Which one?
update your policy? Oh no, oh, the previous one, like the TRPO one. Right. So here you generate samples from the discounted state distribution, I suppose, started from mu. I guess the sample-based version is on the next slide. So for that one, do you assume like any policy parametrization, or this is like optimization in the entire space of policies?
No, so this is the weakness of the paper that was the weakness of the paper that was, we admitted initially that there is no parameterization here. So for this work to hold, your parameterization is what's the so-called natural parameterization of delta to the power of delta of A to the power of S, which is obviously a crappy and horrible implementation.
I see. So can you offer any insight as to how this would generalize to like parametric policy classes, or this really just relies on this explicit connection to mirror descent, and once you add some approximation on top of it, things break? Or I don't know, what's your take on this?
So when you do this is essentially the natural, when you do you compare, essentially do the TRPO with our mirror descent algorithm, and you solve real problems, right? It seems to be working. So the natural extension seems to be working. By all means, this, I'm not saying it's optimal or that it even makes sense. I'm just saying that this is, I mean, in practice, it seems to be working.
Can I add something to that? I mean, like, okay, so there was this unsolicited comment about Polytech. I didn't want to bring it up, but so there, our purpose was really to understand if you bring in function approximation, what happens to the end. So I think that that's kind of what distinguishes these two lines of works. I think here you were going deeper into understanding sort of the dynamics when you don't have function approximation, and in the other work, it was more like the realization that you can add function approximation and these mirror descent type algorithms are pretty relaxed. So the Polytech work actually does, answer to this question in a positive way. Yeah, with some caveats, but work in progress.
All right, so there's a bunch more questions in the chat. So maybe Hake Ishfaq can ask this question, no?
Yeah, so the algorithm for optimistic POMD, it looks very similar to OPPO, and their analysis is for linear MDP, whereas for POMD, it's for tabular case. So I'm wondering if there is any like difficulty in extending the analysis to linear MDP case, or like what's the challenge? Why this is only for tabular case now?
Yeah, so I think a stochastic case is probably, it probably should work. Like, we didn't do it, but it probably should work. For the adversarial case, I don't know how to do it. I mean, if you do, then let me know. But I think it's because
bandit feedback or full information feedback.
For the bandit feedback and the linear case, I'm not even sure how to model things. I think this is a pretty interesting question, but I don't know how to solve it. Like the problem is that the structure does not fit. Whereas in the stochastic case, I think everything should work. But in the online or so-called adversarial case, just the linearities are not there to carry everything through. So I don't know how to solve it. If you know, then let me know. Please send me an email.
Okay, sure.
I will
Thank you.
start to send you an email. Right, so I think maybe Shipra Agrawal had a bunch of questions as well. I don't know if those are answered, but maybe you can ask to Shai, if you're here.
Yeah, hi, Shai. Yes, I think like it's more general question on the setup, and like maybe it's a part of TRPO, not necessarily your setup. So the samples that we are generating, it's from the stationary distribution of mu pi, starting from mu, that you'll reach if you run policy pi, starting from prior distribution mu. So
sorry, go ahead.
so we need M samples, right? And I always wonder, like, why is the sample complexity to get unbiased samples from the stationary distribution now? Is that taken into account or not?
So
Because it may depend on the policy pi that you are visiting as part of your algorithm. You may not have to visit if you.
Yeah. So I think the notion that you sound, I mean, you have an oracle that knows how to sample according to mu, and then, I mean, I do not argue that this might not be realistic, but this is a model. You sample according to mu, and then you play pi k. So yeah, that's I mean that's a common model. We can argue if it makes sense, but sampling from mu is assumed to be possible.
And it doesn't matter if you reach the stationary distribution or not, or any close to it?
No, because remember that you sample from mu, and then you get a state, and then you follow a trajectory. So then you sample, again from mu, and then you follow another trajectory, and you do it repeatedly. So the statistics, I mean, because everything is finite, the statistics work in your favor.
Okay, yeah, so I don't see, like, wouldn't it be biased initially? Like, you want it from the stationary distribution in the end, right?
Well, no, you want it from mu. That's how everything is defined.
Okay.
Everything is defined according to this particular mu, which is a distribution. Yeah. So right. and from a mathematical perspective, like you do the whole thing is done with respect to this particular mu that somebody tells you.
I have another question if I have some time regarding the exploration part.
Yeah.
So I saw that the exploration, you kind of go to model-based a little bit, like you have this optimistic set over the probability distribution.
Right.
So do you think like that's unavoidable, like to do, like, what's your feeling about, I don't know even how to define an adversarial model with probability probability model itself. I believe you assume probability is stochastic and the reward is adversarial.
So once you sort of start counting, I mean, if your question is whether I can Thompsonize, I mean, I don't know. I mean, we tried and we're not successful. But if the question is if I think there's another way to go about it, you know, possibly. I mean, we're happy that we're able to solve it, so to give a solution. So I don't think that I think it's going to be pretty difficult to do anything else, especially for that adversarial model. But you know, I don't know of any other approach that would work, basically.
Okay, thank you.
Mm-hmm.
So maybe I ask a question.
Yeah.
Hi, Shai. This is Amir Masood. Very nice job. So my question is about the use of regularizer, like Bregman divergences. So there is one Bregman divergence that defines the regularized MDP, and then there is another one that is used as a penalty for the mirror descent. And you choose the same Bregman divergence for both of them. I guess one question is that what would happen if you use two different types of Bregman divergences there, and would there be any kind of possible benefits? And I think this kind of a follow-up, this is basically most Chaba's question maybe, or my interpretation of it is that, can you change the lambda of regularized MDP? So maybe you gradually reduce the bias, and what would happen in that case? Like, can lambda be adaptive too?
So to your first question, the reason that you use the same distance is that you'll have this adaptive scaling. So basically, the scaling works out because you have two terms that use the same scaling. I mean, in theory, you don't need to, and you can still run the optimization algorithm, but I don't think that that makes sense, or you'll have to convince me that it makes sense.
Okay.
Regarding the modification of lambda, then I think that's a good idea, and possibly there is something to be gained here, but we haven't done the analysis, so I can't say for sure. But it definitely makes sense to modify lambda. In fact, if you think about it from a more practical perspective, you can consider lambda to be a hyperparameter of your problem. So you basically modify lambda because it makes your solution eventually look better once you solve the real non-tabular approximated version. So yeah, it makes a lot of sense to modify lambda. We haven't done it.
Okay, thank you.
Right. I would suggest that we should stop the official part of the talk here, and we should switch to the